Welcome to the 11th lecture of Digital Image Processing course. In today's lecture, I want to go over some concept on color image processing and see uh, how the technique that we have used and developed so far can be applied to color images. So I start with some definitions and fundamentals of color. Then I will introduce some of the uh, widely used color models. Then I will go over some basic techniques in pseudo-color image processing, and finally more techniques on full color image processing. So in 1666, Isaac Newton discovered that when a beam of sunlight passes through a glass prism, the emerging light consists of a continuous spectrum of colors, from violet to red. So a body that reflects light that is balanced in all visible wavelengths appears bright, but a body that favors reflectance in a limited range of the visible spectrum shows some shades of color. So this is the ranges of wavelength that we have discussed in the beginning of the course as well. As you can see, the visible spectrum is a tiny portion of the full range of wavelength that we can have. So before I continue, let's just review some of the definitions that we had from before as well. We had the definition of monochromatic or achromatic light, which is a light that is void of any color and it's represented only by its intensity or gray level, and it can range from black to white. We have chromatic light, which spans the electromagnetic energy spectrum from 400 to 700 nanometer. And then for any source of color, we can have radiance, which is the total amount of energy that flows from the light source, and it's measured in watts. We have the luminance, which is the amount of energy an observer perceives from a light source, and it's measured in lumens. And we have finally brightness, which is a subjective descriptor of light perception, and it's basically impossible to measure and represents the achromatic notion of intensity. And also, if you remember from the earlier lectures, we said that in human visual system, cone cells are responsible for color vision, and we have three different cone cells for red, green, and blue colors. So now based on that, let us define primary colors and secondary colors. So standard primary colors of light are red at 700 nanometer, green at 546 nanometer, and blue at 435 nanometer. So primary colors do not mean that all visible colors can be generated by primary colors, because what happens with these primary colors is that we have a specific wavelength for each one of them. So creating other colors needs to account for the change in wavelength. So just by adding and subtracting these colors, we are not able to create all the possible visible colors. So in addition to the primary colors, we have secondary colors that are made by adding two primary colors. So we have magenta, which is the result of adding red and blue. We have cyan, which is the result of adding green and blue, and finally we have yellow, which is the result of adding red and green. So in this figure you see primary colors and secondary colors of light. The one underneath is for primary colors and secondary colors of pigments. So there is a difference between primary colors of light and the primary colors of pigment or colorants. So the primary colors of light are basically additive, but primary colors of pigments are subtractive. What do we mean by that? So in pigments, a primary color is the one that subtracts or absorbs the primary color of light and reflects or transmits the other two. So because of that, the primary colors of pigments are magenta, cyan, and yellow, while the secondary colors of pigments are red and green and blue. So basically, the primary colors of light are secondary colors of pigments, and the secondary colors of light are primary colors of pigments. So to distinguish different characteristics of colors, we have these three properties. We have brightness, which is the achromatic notion of intensity. We have hue, which represent the dominant wavelength in a mixture of light waves, or the dominant color perceived by an observer. And we have saturation, which represent the relative purity or the amount of white light that is mixed with the hue. So as you can see, hue and saturation both contain color information, while brightness doesn't have any color information. It only represents intensity. So based on this, hue and saturation combined are usually called chromaticity. So the amount of red, green, and blue to form any particular color are called a tri-stimulus set of values, and are shown by X, Y, and Z. And any color is specified by its trichromatic coefficients, which are basically lowercase x, lowercase y, and lowercase z. They all add up to 1, and each one of them is defined by the ratio of the one of the tri-stimulus values by the sum of all of them. So if you look to the right, you see that this is the standard CIE chromaticity diagram. If you take a closer look, you see that the horizontal axis shows the x-axis, and the vertical axis shows the y-axis. And as you can see, each one of these points in this diagram are represented by a portion of portion of red, portion of green, and also a portion of blue. So to get the portion of the third variable z, what you need to do is that you need to find the value of z based on this equation. So if you have x, if you have and y, z is going to be 1 minus x minus y. So now let's just move to a different color model. So the first and the basic color model that you will see is the RGB model, and each color appears in its primary spectral components of red, green, and blue. So the model is shown in a Cartesian coordinate system, as shown to the right. In this figure, the primary values are at the three corners. So we have red here, we have green here, and we have blue here. And the secondary colors, magenta, yellow, and cyan, are at the other three corners. So in this cube we have 8 different corners. So then we have 3 of them for the primary colors of light, and 3 corners for the secondary colors. So what we need is 1 corner for representing the black, which is the origin, basically the location where the amount of red, green, and blue are 0. And then we have white, in which we have red, green, and blue to be at the maximum. As for the grayscale, is represented by the line connecting the black corner and the white corner, and this line contains all the color values for which the amount of red, green, and blue are exactly equal. And it is shown, as I said, as the line connecting the black corner and the white corner. So each one of these colors can be represented by a specified set of bits. So for any color image which is shown in an RGB model, we have 3 color components, and if each one of them uses 8 bits to represent the range of the values, we end up with a 24-bit RGB color cube, which can be shown here. So we have other color models as well. CMY is the second color model that I will introduce here. So RGB works based on the primary colors of light. CMY uses the secondary colors of light or the primary colors of pigments, which are cyan, magenta, and yellow. For example, when a surface coated with cyan pigment is illuminated by white light, no red light is reflected from the surface, since cyan subtracts red light from the white light. So to go from RGB to CMY, you need to do this simple calculation. So cyan is 1 minus red, or magenta is 1 minus green, and yellow is 1 minus blue. So considering 1 is basically R plus G plus B, you can clearly see that each one of the secondary colors of light can be derived by adding two primary colors of light. So equal amounts of pigment primaries should produce black, but in practice, since we don't have pure colors, this is not satisfied, especially since a CMY color model is used for printers. So the result of adding cyan, magenta, and yellow with equal amounts is not usually pure black, but it's like a muddy brown. So what happens in practice is that a fourth color black is added and is shown with K. So that's why we have CMY and CMYK color model. So CMY only has 3 color components, while CMYK has an extra color component that shows black colors. And the next very common color model that we describe here is HSI. So RGB and CMY color models are not well suited for color description for practical human interpretation, because humans describe colors by hue, saturation, and brightness, not necessarily by specifying the percentage of red, green, and blue combined to create a specific color. So if you remember from a previous slide, we said that there are 3 distinguishing characteristics of color. We have brightness, which doesn't have any color information, and it's the achromatic notion of intensity. We have hue, which is the dominant color perceived by an observer, and finally we have saturation, which shows the relative purity of the amount of white light mixed with the hue. So based on this, we can derive HSI color model. H stands for hue, S stands for saturation, and finally I stands for intensity or brightness. So in HSI color model, we decouple the intensity component from the color carrying information. So to do that, we have to derive some specific equations to be able to convert from RGB to HSI. So even though the derivation is very straightforward, the final results are a bit more complex than when, for example, you wanted to convert from RGB to CMY. So here I'm not going to go over the detail. You can refer to the book or any other resource to see how these equations are derived. So as you can see, for the hue, we have basically a range of degrees changing from 0 to 360 that is designed to show all the colors. For the saturation, the equation is designed to be able to extract the amount of white light that is mixed with different colors. And finally, for the intensity, which is the simplest one of the 3 color components in the HSI model, we basically calculate the average of red, green, and blue. So here in this figure, you see the HSI components of the 24-bit color cube that you saw in a previous uh, slide. One thing that you may notice instantly is that we have this discontinuity in the presentation of hue that can introduce some major challenges when we want to um, uh, process color images that are represented in HSI color component. But again, HSI is more intuitive when compared with RGB, because the way that humans describe different colors is more aligned with the color model of HSI rather than RGB. And another thing that you might notice here is that for driving the equations for HSI and converting from RGB to HSI, we use a cosine function, and also we use a mean function, which basically introduces nonlinearity in the derivation of these equations. So this is another thing that needs to be considered. Of course, these are only the equations when you want to convert RGB to HSI. If you want to convert from HSI to RGB, you will need to use a different set of equations. Fortunately, all these conversions are pretty standard. So if you're using MATLAB, for example, and the image processing toolbox, there are readily available functions that can do the conversion for you. And by no means the color models that I just described are the only color models. So there are different color models that you can look for them online. So now that we have learned the basics of colors, let's just see how color image processing can work. So the first thing that I want to talk about is the concept of pseudocolor image processing, in which we work with grayscale images, but what we do is that we assign colors to gray values based on a specific criteria. So why do we do that? The reason is that humans can distinguish thousands of different color shades, while if we are only considering grayscale values, humans can only detect and distinguish around 24 shades of gray. So because of that, and in some applications, it's better to convert the grayscale image into a pseudocolor image for better visualization. So intensity slicing is the simplest method in pseudocolor image processing. In this technique, the range from black to white grayscale values are divided into sections, and for each section a different color is assigned, and the image is represented using these pseudocolors. So here you see one example. We have the grayscale image of a patient. Basically, it's a medical image, and to its right you see the result of intensity slicing using 8 different colors. And as you can see, even though there are some regions in the image that are not visible in the grayscale, when we do intensity slicing and create these pseudocolors, we are able to distinguish between even the slightest variations of the intensity in the pseudocolor image. Here you can see another example. On top you see a grayscale image that is captured by a special type of radar that measures the average monthly rainfall. So one application of pseudocolor image processing is basically to assign colors to these different gray values. So the one on the bottom is basically the set of the pseudocolor image produced based on this color map. And as you can see, when you compare this image with the one above, you're able to better visualize the amount of rainfall as opposed to if you only had a grayscale value. But pseudocolor image processing is only a small part of color image processing. So because of that, let's move to full color image processing. So full color image processing usually consists of two categories of techniques. In the first category, you process each grayscale component individually, or each color component individually, and then form the composite color image. And in the second category, you process the color pixels directly. So the color pixel can be shown as a vector. So any pixel in a color image is shown with a vector of different number of values. So in this image, you see an example of a grayscale image. We have pixel X and Y at the center of this two-dimensional neighborhood. And for each one of these pixels, we only have one value that represents the intensity. Now on the right, we have, for example, an RGB color image, in which for the same pixel location X and Y, now we have a 3D neighborhood. One dimension is along the horizontal axis, the other dimension is along the vertical axis, and we have a third dimension that is along the color axis. So for any individual pixels, we have three different values, one showing the amount of red, the other one showing the amount of green, and the other one showing the amount of blue. So if you're working with RGB, with CMY, and with HSI, for each pixel you have three color values. If you're working with CMYK, for example, for each pixel you will have four color values. So here you see another example, and this is the original full color image that we have. These four are the four different components of this image. If we use a CMYK color model, this one is representing cyan, this one magenta, this one yellow, and this one black. The next row is the same image but is represented with an in RGB space, and finally the last row is for representing the image in the HSI color model. So now that we have learned how different color models can be represented, let's just start with a basic set of transformations. These are the transformations that we saw in the earlier lectures of the course. So the color transformation can be modeled as this simple equation: Si equals Ti of Ri for I changing from 1 to n. So here n is the total number of components in the images, or color components. So for example, if you are working with RGB images, n is going to be 3. Ri are the intensity values of the input component images, and Si are the spatially corresponding intensities in the output component images. And finally, Ti are the set of transformations or color mapping. As I said, n is going to be 3 if you're working with RGB, CMY, and HSI, and it's going to be 4 if you're working with CMYK. As you can see here, for the transformation or the color mapping, we have T subscript I. So that means that T can be different for each color component. So it doesn't have to be necessarily the same for all the color components. So even though any transformation can be performed in any color space, some operations are better suited to specific models. So this is an example that we will see later on as well. So some of the procedures, for example, smoothing or sharpening, right? Without any problem you can do it in HSI or RGB, right? But if you want to do segmentation, it's probably better to be done in RGB model rather than in HSI. So you will see later on different set of techniques that can be used. So for example, let's just modify the intensity of an image with a constant value k in the range 0 and 1. So basically we want to scale the color components of an image and see what happens. So in the HSI color space, what we only need to do is that we only need to modify the intensity component. So the first two components, the hue and saturation, they remain the same, while the third component is multiplied by K. In RGB color model, you modify all three components by the same constant. So S1 becomes KR1, S2 becomes KR2, and S3 becomes KR3. Just keep in mind that each one of these S's, depending on the color model, means different things. So for example, if you're working in HSI color space, S1 means hue. But if you're working in RGB, S1 means red. In CMY, all three components are modified similarly as well, right? But now the equation that you use for modification is a bit different than RGB. So you can drive this simple equation on your own, but basically keep in mind that RGB is working based on the primary colors of light. As we saw, they are additive, while CMY works based on the primary colors of pigments that are subtractive. And finally, if you want to do the same transformation in the CMYK color model, the first three components, basically cyan, magenta, and yellow, remain the same, while you only apply the transformation to the black component of the CMYK model. So let's just see how these transformations can be seen in practice. So here on top left we have the original image, and on top right we have the result of applying this transformation. On the bottom we see the different types of functions that you need to apply. So if you are working in RGB model, basically the same transformation is applied to all the color channels. If you are working in CMY, again the same transformation is applied to CMY channels. If you are working with CMYK, these two set of functions is applied. So you modify the K while CMY stays the same. And if you're working in HSI color model, H and S stay the same while you apply the coefficient K into the intensity component. So now let's take a look at another color transformation, more specifically color complements. So we can create a color circle or a color wheel, which is a visual representation of colors according to their chromatic relationship. So this is an example of a color circle. So hues directly opposite one another on the color circle are complement. So for example, red and cyan are complement, blue and yellow and magenta and green and anything in between. So in RGB color model, the implementation of color complement is very straightforward. So if you have R out, G out, and B out as the three color components of the result, they can be calculated by subtracting a matrix of 3 by 1 and the color component of the input image. The same can be said about the CMYK as well, but in HSI color space, the complement transformation is not as straightforward. And the main reason is that the saturation component of the complement cannot be computed only by the saturation component of the input image. Remember, for calculating the saturation component, what we had was we used the three red, green, and blue components, right? And we used a nonlinear mean function as well. So all those three components were combined to create the saturation. So because of that, you cannot calculate the saturation component of the result only by the saturation component. That's why as I said before, some of the transformation is better suited for some of the color models. So the implementation for the color complement in the HSI color model are as follows. H out, the hue component of the final result, is calculated by these two part function. Depending on the value of hue, if it's between 0 and 0.5, the output is going to be the input hue plus 0.5, and if it's between 0.5 and 1, the output hue is going to be the input hue minus 0.5. As for the saturation, as I said, we cannot calculate the saturation component of the complement image from the saturation component of the input image, so we cannot get the true saturation component, so we just simply put it as what it was before. And as for the intensity, we just subtract it from value 1. So here you see the original image that we want to calculate the component for it. This image shows the set of transformations that you need to apply. If you are working with RGB color model, this is the transformation that you need to apply to all of the channels. If you are working with HSI, these three transformations are the one that you need to apply. So you need to apply this transformation to the hue component, the saturation component stays the same, and finally the intensity component can be calculated by this specific transformation. So now this is the result of calculating the complement of the input image in the RGB model, and this one is the result of calculating the complement of the original image using HSI model. As you can see, they are mostly the same. Of course, there are some differences between them as well, and the reason for that again is because the saturation component cannot be directly calculated only by the saturation component of the input image. So in terms of accuracy, you can say calculating color complement in the RGB model are more accurate, but visually speaking, there is not that much difference between the results. What about color slicing? So color slicing is a technique that is used for highlighting a specific range of colors to display. So if the colors of interest are shown by a cube or hypercube, if you are working with a color model that has more than 3 dimensions per pixel, and this cube has a width of W that is centered at color A1, A2 all the way to AN, the transformation that you need to perform is represented in this equation. So even though it might look very complex, in reality it is not that complex. So what you basically are doing here is that you define a hypercube or a cube in the color model, in the color domain. Whatever color that falls inside of this cube is preserved, while any color that is outside is replaced by a constant value. You can do this similarly by considering a sphere or a hypersphere. Here what you have is basically a sphere in the color space with radius r0, and the center is at A1, A2 all the way to AN. And here whatever color that falls inside this circle that is shown with this equation remains the same, while any color that is outside this range is replaced with a constant value. So here you see an example of color slicing transformation. On the left one, we are using a cube with width 0.2549 that is centered at this location, and the one to the right is using a sphere of radius 0.1765, and the center is basically uh, the same as with the cube. And the goal here was to detect all the red colors in the image. So what about tonal and color corrections? So typically the same transformation function is applied to each component in the RGB and CMY model. For HSI only you need to change the intensity component, and you leave the saturation and hue components unchanged. So on the right you see some examples of color correction that is done in RGB model. So the image on top left is basically flat with low amount of contrast. By applying this transformation to the RGB color component, this is the image that you get. The second example is an image that is very bright overall, so again has low contrast. By applying this exponential color transformation to all the three components, you get a result that looks like this. And the last one is an image that is generally dark, and if you apply a logarithmic color transformation function to all the color components, red, green, and blue, this is the image that you get. Here is another example of a color correction that is done in the CMYK color space. On top left you see the original image, and then the rest are the result of applying different types of transformations to different components of the image. So if you apply an exponential function onto the black component of the CMYK, you get an image that is generally darker, or if you apply a logarithmic function onto the black component, you get an image that is generally brighter. So you can analyze the rest based on the individual color components as well. So what about histogram processing? So if you remember, we did introduce two techniques for histogram processing. So we did histogram equalization and histogram matching. So what about color images? So histogram processing of individual color components is not usually recommended. In HSI color model, what we usually do is that we only process the intensity component of the color image and leave the hue and saturation components unchanged. So this is an example of performing histogram processing, or like any processing on an image, in which performing that in HSI color model is more preferred than performing it in RGB color model, for example. So on top left you see the original image, in which it has poor contrast. For example, these regions, there are some details that are not visible that much. By doing histogram equalization and applying this transformation function to the intensity component only, this is the result that we get. And as you can see, the contrast of the image is generally improved. But as discussed in the book, the result of only processing intensity component causes the colors to be a little bit less saturated. So what can be done later is to slightly modify the amount of saturation, as is shown by this transformation function, to make the colors more vibrant. But this is an additional step, so depending on the type of the image that you have, you may not need to do this additional step, and only you need to do histogram processing on the intensity component only. What about smoothing? So in RGB color space, smoothing can be done on all the individual color components. So you basically apply the same smoothing kernel on the red, green, and blue components. In an HSI color space, the intensity and color information are decoupled. So because of that, you can only smooth the intensity component of the image and leave the saturation and hue unchanged. So as you can see here, on the left we have the result of image smoothing by applying a 5x5 averaging kernel to the red, green, blue component of the image. In the RGB color model, this one is the result of applying the same 5x5 averaging kernel, but only being applied to the intensity component because this image is processed in the HSI color model. When you look closely, you don't see any significant difference between the results of the two processes. So one thing that you can do is that you can calculate the difference between the two results and see if they are that different. So if you look at the difference, you see that the results are practically the same because the amount of difference is very close to zero. What about image sharpening? The same can be said for image sharpening as well. So in RGB color space, you can apply the Laplacian operator on each one of the individual color components in the RGB color model. In the HSI, again, since the intensity and color information are decoupled, you can apply the Laplacian only to the intensity component and leave the hue and saturation components unchanged. Again, the image on the left is sharpened using Laplacian that is applied to all three red, green, and blue color components. The one in the middle is the result of applying the Laplacian only on the intensity component of the color image. Visually speaking, there is no significant difference between the two, and if you calculate the difference image, you see that the difference between the result of these two procedures is practically zero. What about segmentation? So in HSI, what is common is that saturation is used as a masking image in order to isolate regions of interest in the hue image. So the intensity image is less common since it does not carry any color information. So let's just take a look at one example. So one thing that I should tell you now is that this example is very subjective. So if you see multiple steps that are being performed, the main reason for that is the procedure is very subjective. So here what we have is we have the original color image in which we want to segment the regions that have a red color, so basically these regions. So this image to its right is the hue component. This image to the bottom left is the saturation component, and this one is the intensity component. So these three combined represent the HSI components of the original image. So now we have this image which is the binary saturation mask that is created based on the saturation component of the image. In this image, black is representing 0 while white represents 1. Now in subfigure F we have the product of B, this component, the hue component, and this mask. So now what you see is that if you create the histogram of this image, this is the histogram that you get. So now you can use basically segment the red components of the image based on this histogram. So let's say you apply some a threshold that can segment the red component of the image. So this is the result of segmentation of the red colors in the image. So now let's see how this can be done in the RGB color model. So even though working in the HSI color space is more intuitive, because again, as we said, HSI color space is based on the way that humans describe different colors. Segmentation is generally better if done in RGB color space. So the way that we can do it is that we provide to the algorithm a set of sample color points for the color of interest, and these sample color points are then averaged and then used as the center for the area that we want to that the area in the color space that we want to segment in the image. So now that we have these colors of interest, sample color points, we can use a distance function to measure the distance of all of the color points to the color of interest, and then segment the image by applying a threshold onto that distance. So here what we have is that we have the original image in which this box shows some sample color points. So we take the average of the colors in this region in the RGB color model, and if you look closely, we can represent this average at the center of a greater region that we want to use to segment. So we can use any of these shapes to basically single out the colors that are closest to the average that we want, and by applying that we can do a better segmentation of all the regions and that contain red color in this specific segmentation example. What about image gradient and edge detection? That was an important topic that we have seen several times in the discussions that we had. So the gradient discussed before for edge detection of grayscale images cannot be applied directly to color images. Why is that? Because it was not defined for vector quantities. So if you remember, for grayscale images, for any intensity value we had, for any pixel we only had one value that represents its intensity. So in other words, grayscale images are scalar images, while color images are vector images. Why? Because for any given pixel we have multiple values that show the amount of different color components. So now to calculate the gradient on color images, we assume lowercase r, lowercase g, and lowercase b as the three unit vectors along the red, green, and blue axis of the RGB color space, and then we define these two parameters. We define u, which is basically the vector showing the amount of derivative of each one of the color components with respect to x. So we have u equals the derivative of r with respect to x multiplied by the unit vector in the direction r, plus the derivative of g with respect to x multiplied by the unit vector in the direction g, plus the derivative of b with respect to x multiplied by the unit vector in the direction b. And you do the same for v as well. So the only difference here is that you are calculating the derivative of the color component with respect to variable y. So now that we have u and v, we can define g of xx as the dot product of u and at itself. We have g of yy as the dot product of v and itself, and finally we have g of xy as the dot product of u and v. So if we do this dot product and we simplify the result, g of xx is basically the squared sum of all the individual color components derivative with respect to x, and g of y is the squared sum of all the individual color components derivative with respect to y, and g of gx r basically is the summation of uh, derivative of r with respect to x multiplied by derivative of r with respect to y plus derivative of x and g with respect to x multiplied by derivative of g with respect to y, finally plus derivative of b with respect to x, derivative of b with respect to y. So now based on these defined quantities, we can define the direction of the maximum rate of change of c of x and y. C of x and y is basically the color image as this equation. So this is representing the direction of the maximum rate of change. Theta of x and y equals 1 over 2 arctangent of 2 g of xy divided by gxx minus gyy. And also the value of the rate of change in this direction is defined based on this more complex equation. So these equations associate with each point x and y in the color image a pair of orthogonal directions, where along one of them f is maximum and it is minimum along the other one. So as you can see, the derivation of the gradient equations for color images is a bit more involved than it was for the grayscale images. If you are interested, you can refer to the original books or papers that drive these equations in much more detail that I discuss here. So now let's just take a look at one example. So on top left you see the original red, green, blue or RGB image. On top right you see the gradient that is computed in the RGB color vector space using the equation that I just described. This image is the result of calculating the gradient image that is formed by element-wise sum of 3 individual gradient images. So basically what we did was that we calculated the gradient images for the red channel, the blue channel and the green channel, and then we summed all of them together to create this image. As you can see, when you compare these two, generally speaking, they are very similar, but if you calculate the difference between the two, you see that they are basically very different too. So depending on the different application that you want to use these gradients, in some cases maybe just performing it using calculating gradient image for each one of these individual color components and summing all of them together can be done much faster than doing it the other way, right? So if you want to have a good estimate of the edge components, maybe you can get away with only doing it this way, so you have an approximate of the gradient values. However, for some applications which you require the accurate value of the gradient image and also you want to know the direction of the gradient, then you probably need to go the hardest route to calculate the gradient image in the color vector space. And underneath you see the components of gradient images of the color image. This one is the gradient image that is calculated using the red component. This one is using the green component, and finally this one is using the blue component. And as you can see, they're in different in any of these images there are some regions that are not present in the other images. For example, if you look at this region for the gradient image of the red component and you compare it with the gradient image of the green and blue component, you see that you see more detail that are present in the green and blue component while it is missing in the red component. You can you can see the same thing in this region around the nose, that the gradient image that is calculated based on the red component is not able to detect any edges, because in terms of red color there is no difference between the neighboring pixels that show the edge around the nose of the person in the image. What about noise in the color images? So usually the characteristics of noise are similar in all of the image color component, but this is not always the case. So for example, if you are using a red filter when you're capturing a camera, definitely the noise characteristic will be different in the red components rather than the green and blue components. So generally speaking, fine grained noise is less visually noticeable in color images than it is in the grayscale images. So let's just take a look at one example. So on top left you see the red component of a noisy image, top right you see the green component, and bottom left you see the blue component of the noisy image. And for each one of them we have a Gaussian noise of average 0 and a standard deviation of 28 intensity levels. And finally, this one is the result of RGB image that is created by these three noisy components. So now what do you think happens if we convert this RGB image into HSI? So converting an RGB image to an HSI causes significant degradation of the hue and saturation components when you have noise, because the nonlinearity of cosine and minimum functions in the conversion process. So what happens is that if you have a noisy image in RGB color model and you convert it to HSI, usually the hue and saturation components look worse than if they were for a noise-free image. Not only because of the linearity, but also, if you remember, the hue component had a discontinuity as well. So this is the result of converting the noisy RGB image from previous slide to HSI color model. While the hue and saturation components look worse, the intensity component is slightly smoother. Why? Because to calculate the intensity component, we basically take the average of red, green, and blue. And if you remember from the earlier lectures of the course, we said that if we have a set of noisy images that have independent noise, if we take their average, we basically eliminate noise while we increase the amount of signal. So by this I conclude the lecture on color image processing. In the next lecture I will give you a brief introduction to image compression and watermarking. We talk about some fundamentals of image compression. I describe different types of redundancies that you can have in images or sequences of images. I will show you ways to measure image information, how to measure the fidelity of image compression algorithms, then briefly go over image compression models, and then some notes on image coding and image watermarking.